Monday, and I have a government legal test on Thursday. So see how my weekend goes. My friends want to go this weekend. How do you know now? I don't have no one. I'm like, are you going to my class? Are you going to do homework? My kids, I have my homework. And a lot of it is like work, yes, so I have to time. Some of the homework I have. Yeah, so. Yeah, that's actually. I'm lazy to read everything. For me, this is actually really easy. The one that I will have trouble with chapter. On the exam. I like this. Three?
Yeah, we're different.
Yeah, I'm just real. No, I did all of them. I just didn't do all of them. Prop word models. No, I kind of did all of them. Oh, that chapter. Oh, the cheating part. Oh, yeah. I just worry about chapter. I haven't done my counting. On Tuesdays. It's good because when you make this and all the homework until like the exam date, so all I do is time. Yeah, it does fine. I used to hate these. I only miss. This is the nonsense, so that would be. I try to do all of it. Yeah, I was in the I turned solid to it. It's a little stuff. Adults. Yeah, I turned solid to 6 months. I didn't turn to it because it was just a whole. And I think it's a quiz on my phone. Not for.
All right, folks, let's all come back together. Now, we have an hour and 25 minutes. We will continue to plug along and see how to compute monetary values under different interest rate scenarios. And we'll get as far as we can, and then wherever we stop, that's where we stop. Right? So I won't hold you accountable to anything that we don't get to tonight. So I do want to try to get as far as we can. So I might start skipping around a little bit with these problems. And at popular request, if I skip it, then that means you can cross it out. How's that sound? Okay. So let's take a look here. If inflation is 4% a year compounded annually, what will it cost in 25 years to buy a house that's currently valued at $74,000? How do we just set up the problem? Let's just talk about that. How do we just set up the problem?
Compounded annually. So we're using that A equals 1P. Is that the one we're using?
Yeah, we're using the compound interest. And we know the interest rate is 4%. It's compounded annually, so n equals 1. What will it cost in 25 years to buy a house that's currently $74,000? So what do I put where?
Is P the same?
P that is the $74,000, which is going to grow over time because of that 4% interest rate. And they're saying, how many years? Oh yeah, 25 years. So just by computing that, that's telling us the value of the home later, right? So even though this might feel like it's a different question because we're talking about the value of a home, we are nevertheless talking about inflation, we're talking about interest, and so that's how much the home will cost 25 years from now. And I'm satisfied going that far. Let's just set it up, see how we're setting up and why, and then we'll just keep going. Is that okay? We do that? Because really, we don't have to do all these computations. What we need to do is just see how to set up the problem. Okay.
Yes, we can turn
Well, I mean, you should type it into your calculator, but I'm not going to right now. Let's just keep going and talk about setting these things up. So how about 24? Another interesting question. A small company borrows $70,000 at 4% compounded monthly. Why did they borrow the $70,000? Why did a company borrow money?
For buildings.
Exactly. They needed to build something. They needed a new machine. They needed to renovate. They needed to make it look better on the inside. So they borrowed $70,000, and the loan is due in 10 years. How much interest will they pay? So what does that mean? 10 years from now, they have to pay back the $70,000. They got to roll up to the bank and be like, hey, here's that $70,000 you gave us. But also, here's the interest we owe you. So how do you set this one up?
10 years, 70. Doing 10 years, interest.
Is it essentially the same setup? They're borrowing the $70,000. It's going to earn, it's going to build and accrue interest at 4% for 12, monthly for 10 years, and then whatever that A is, that's how much money they have to actually give back to the bank.
Well, no, don't we do because it's just the interest that will be okay.
This is the loan is due in 10 years. How much? Oh, how much interest? Yeah. So once you get the answer, you would subtract out the 70,000. That's how much interest you have to pay.
Okay, so it's raised to 100. So you just plug that all into our calculator and subtract 70,000 from it?
Yep. Yeah, because you're doing the amount and then subtract the 70,000, and that's just how much interest. Now, obviously, they don't have the money to pay back now. They just use the money to buy equipment. So they're going to pay back everything 10 years from now. They're going to walk over and hand them this amount. But in case you were curious, you're just calculating how much of that is interest. Yeah. Okay, so that's 24. Number 25 is so basic. Let's just skip it. Andrea Guilford. Come on. That's a trick question. Nobody's name is Andrea Guilford. And it just says she has a savings account of $27.59 after 4 years. How much will she have? That's a real basic question. We've already solved problems like that. So cross that one out completely. Cross out 25 with the fury of your joy.
What number?
20, go ahead. Nora Ortega. How did I do that? Nora Ortega? Is that what you said?
I mean, you misspelled the name, the last name.
I didn't misspell anything. That's from the program.
Oh, the program misspelled the name then.
Why? What should it be?
No, no doubt. Ortega. Well, you said Ortega, but it's actually written Ortega.
Oh, Ortega. That's true. Ortega. Okay. So, wait, that must be what it is. Her savings account has that balance after years, eight years. What will the amount? This is a basic problem. Cross it out. Right? Don't we totally know how to do this one? That's just the compound interest formula. Okay. Barbara, trick question. No one's maybe. Okay, I like that joke. She knows. Okay, this is a good question. She knows that she will need to buy a new car in 2 years, and the car will cost $15,000 by then. So, in the future, A is $15,000. That's the amount she needs 2 years from now. How much should she invest now at 5% compounded quarterly so that she'll have enough to buy a new car? Nick, tell us all the answer.
No.
Yeah, it's $14,999, right? Oh, that's great. All right, so but Rick, how much does she have to invest now? Well, we don't know, but we want $15,000, and so we have to invest some principal now, so that we would have what is the interest of 0.05, and it's compounded how much?
Quarterly.
Quarterly, so 4 times, and it's 2 years from now. Well, there we go.
What they invested in, like stock or something, just put it in the savings account. That's crap, you know.
Oh yeah, it's not very good interest.
The money you're going, invest, you just save, add to it. You get to your final amount faster.
Yeah.
Not that, but what car costs $15,000?
Yeah.
You what?
I said, what car costs $15,000?
A used car.
Yeah.
A used car. My wife's younger brother, he just got a really nice Volkswagen something car for $10,000.
Yeah, I know.
Yeah.
My mom got a pretty good one for like 9, 8.
Yeah, yeah.
For a brand new?
No, not for a brand new one.
No, yeah.
You get a small car.
Okay, a small car, yeah. Okay, so everyone sees how to solve it? Okay, you multiply all this stuff out and then divide it off of the P. Okay. 28. Southwest Dry Cleaners believes that it will need new equipment in 8 years. Okay, this is a good question. They are going to need equipment 8 years from now. So in 8 years, our equipment's going to be old, broken. We'll need to buy some new stuff. The equipment will cost $26,000. That's in the future. It would cost $26,000. What lump sum should we invest now so that we have 26,000 later. So what would we write down? And what's n equals if it's compounded semi-annually?
2.
Yeah, 2. And how many years later? 8 years. Okay. Is that what everyone got? Really, which formula are we using every single time? Same formula. But we're just deciding where to put the numbers. And I think one thing to help us out is that this is, the A value is the future, and the P value is now. Right? That's helpful. P is the present, the principal in the present, and A is the future amount. Okay, so that's 28. Yay, so here we are on section 5.2. Now, everything that we've done up to this point has been about lump sum investing. What is lump sum investing?
One big amount.
Yeah, just one principal, boom, you stick it in the bank and then you walk away and you don't think about it for a few years. That's lump sum investing. Now we're going to talk about annuities. And annuities, as strange as that word is, annuity, means you keep on putting money in every month. Normally annuities are monthly, but annuities can also be yearly. The point is you keep on putting in money. It's not just one lump sum. An annuity means regular investments. So annuity is regular, periodic investments, as opposed to a lump sum. In order to understand what that looks like, we have to at least be a little familiar with the idea of a geometric sequence. In an arithmetic sequence, so let's just contrast. In an arithmetic sequence, you add the same thing over and over and over again. So an arithmetic sequence is like just counting by 5s. 5, 10, 15, 20, 25, 30, and so on. What am I doing every single time?
25.
You just add 5. A geometric sequence is very different because you start with a given term, and then you multiply by the same number over and over and over and over. So I'm going to start with 2 and then multiply by 2. So times 2 is 4, times 2 is 8, times 2 is 16, times 2 is 32, and so on. So that's a geometric investment. And what I'd like us all to imagine is, let's say that we are getting interest compounded monthly. And the amount of interest that we're actually getting compounded monthly is 2%. So I just want you to imagine that right now, last month, this is February, let's pretend it's January. In the month of January, right, we'll say at the end of January, so that's fine, January 31st, we've put $100 into the bank. Well, I guess it would be at the beginning. No, it's going to be at the end. We put $100 into the bank. I haven't decided if it's in the beginning of January or the end of January. No, it would have to be the beginning. So, bam, on January 1st, we put some money in, $100. Now, at the beginning, it's technically at the end of every month. It's just such a bummer to write this down. If you put the money in, then on January 31st, they're going to go ahead and give you 2% interest. So what would I write down? 100 times 1.02. That's now how much money I have at the end of January. I put the $100 in on January 1st, but after 1 month has gone by, they're going to go ahead and give me 2%. And that's that compounded interest they're going to start putting into my bank every month. So at the end of February, now February 28th, now how much money do I have in my account? 100 times 1.02 squared. Because they have now multiplied times 1.02 twice. And that has increased how much money I got. So how about at the end of March, how much money do I have in my account? Oops, that's a 2. Now at the end of March, I have 100 times 1.02 cubed, because they have now multiplied my money 3 times the 1.02 to give me 3 compounded interest amounts. Well, you can kind of see what's happening. This is the 3rd month, right? So by the 12th month, by the end of December, how much money do I have? Yeah. And this is technically a geometric sequence because every single time I'm multiplying not times 2 times 2 times 2, I'm multiplying times 1.02, times another times 1.02, times 1.02, times 1.02. And that's watching our money grow. So everyone, have fun on your calculator. Type in 100. Type in 100. You hit 100, enter. 100, enter. Then do times 1.02. And that takes us to January. The end of January. Now I have $102. And now you should just be able to hit enter, 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 but count as you go. So that was January, February, March, April, May, June, July, August, September, October, November, December. Did everyone end up with 126.82? Okay. So that's really what compounded interest looks like. So they're putting in a little more, a little more, a little more, a little more every month, and they're giving you the interest on top of the amount that you have. So you're not earning interest on the $100 every month. This month you earned interest on $100. This month you earned interest, this month you earned interest on $100. But the next month you earned 2% on the 102. And the next month you earned 2% on the 104.04. And the next month you earned 2% on the 106.12. So you're actually earning interest on the interest that you already earned. Okay, well that's it. This is the notion of a geometric sequence. And they gave us some problems here about geometric sequences. And honestly, I don't think we even need to really get into this. This is kind of like old math that you might have done in another class. We don't have to focus on it. I just want to make sure we all know what's happening every single month. And what's happening every single month is that you're multiplying times the interest rate. So cross out 29, 30, 31. Now this one's interesting. 32, 33, and 34. It says to find the sum of the first 5 terms. So we're going to do this manually once, just to see how it works. Number 32, they're telling us that the first term is 3. Technically, that should be like a sub 1. The first term is 3. And what are we going to multiply over and over and over again? 2. R equals 2. R is the rate that you're multiplying by. Normally, we'd multiply by like 0.02 or 1.02. But they're just saying, go ahead and multiply times 2. So if the first term is 3, what's the next term? 3 times 2. 6 times 2 again. Times 2 again. Times 2 again. Now we want to find the sum. It says find the sum of the first 5 terms. 1, 2, 3, 4, 5. So you add them all together. But watch. Technically, this was 3. This was 3 times 2 to the first. This was 3 times 2 to the second. And this was 3 times 2 cubed. And this was 3 times 2 to the fourth. And if I put a little plus sign in between all those, what can I do with all those 3's? I can factor it out. And then what I really have is 1 plus 2 to the first plus 2 squared plus 2 cubed plus 2 to the fourth. And it just so happens that there's a formula for finding the sum of a geometric sequence. You don't have to sit there and type it all into your calculator. There's a formula that tells you what that is. So that's what I'm going to show you right now, just to put it in perspective. Let's just forget about the 2 and go back to saying this was the amount, the 3 that I started with. And that's 1 plus the rate plus r squared plus r cubed plus r to the fourth. That's really what we're finding. Whatever you started with, your principal, and then all these interest rates. Now, does this look like the January, February, March problem now? I invested the $100, and then I multiplied times 1.02, and then 1.02 squared, and then 1.02 cubed, and so on. Well, the formula is, if you want to jot this down, is A, I think they're going to have it. I want to write it down the way they have it. So it's, we're all using the same. Well, here's how they have it. A, r to the n minus 1 all over r minus 1. Where r represents the total number of, where n represents the total number, not the exponent on the last one, but the total number. So 1, 2, 3, 4, 5. So let's see if that worked out. and we should confirm that. So if I actually add up those terms, 3 plus 6 plus 12 plus 24 plus 48, the sum should be 93. And if I do down here 3 times 2 to the 5th minus 1 over 2 minus 1, yeah, oh goody, it worked. Well, this was just a little fun exercise in arithmetic to show that the formula works and what we're even calculating. We're technically doing the sum of a geometric sequence where what's our R value always going to be? The interest rate, which is technically, if it was 2%, would that R be a 0.02 or a 1.02? 1.02, because that's what we're really multiplying by over and over again. So we have this formula now, which we can use to calculate the sum of a geometric sequence. And that's pretty fun, because, well, I wish I hadn't erased it, but if you took your $100 and then your $102 and then your $104.04 from, that was January, February, March, and April, and so on, we could have very quickly added up how much money we'd have at the end of the year. And in fact, we can still go ahead and do that. Let's say that we're going to do, this is our first annuity problem. We're going to do an annuity in which we invest $100 at an interest rate of 2%, and we'd like to know how much money we'll have. Well, technically that's how many times we put it in January. Well, we haven't even modeled that. We haven't even looked at what this means. All we did was just look at how much that $1 amount looked like. But if we were to calculate our annuity, we didn't talk about this yet. Well, let's just go ahead and do it anyway. This is going to tell us how much it all adds up to. I need to make it clear how this works. I have to draw a little calendar for us to look at this, because it's kind of crazy. Here's January, February, March, April, May, June, July, August, September, October, November, December. There we go. So if I invest $100 in January, how much will it be worth by the time it gets to December? But the $100 that I put in January, how many times will it have earned interest? 12. So then I'd have 100. Actually, technically, if I put the 100 in now,
If you do it on January 1st, it still counts.
Well, that's true. It's at the end of each time period. Well, either way, this one would have earned interest if I put it there January, then once, twice, 3, 4, 5, 6, 7, 8, 9, 10, 11. So we're going to say 11. So it earned 2% 11 times. So that's the $100 I put in February. That's how much it'll be worth by the end. If we're saying that you didn't technically earn interest the first time, but you had to wait until February, maybe on February 1st, then you got it. Okay, what about the $100 I put in February? How much will that be worth by the end?
100 times 1.
Yeah, because that one will have only earned 10 rounds of interest. And then the $100 I put in March?
Times 10 to the times
Yeah.
10 to the negative.
So you can see what's happening here. Until finally, how much will the $100 be worth that I actually put in December? Just the 100, because it didn't even have a chance to earn any interest. So what we're going to end up with our annuity is a sum of all those $100 that we put in every single month, but each of those $100 will have been in there at different amounts of time, earning a different amount of interest. So the money that we put in the earliest gets the most interest, and the money that we put in towards the end gets very little to no interest. So now this is what we're adding together. And so now we can go ahead and use this formula and see how much our annuity will be. So let's try it together, folks. We're going to use this annuity formula here. And what's our A value? How much are we putting in every month? 100. And then our rate is 1.02%. And then N is the total number of investments we did, which the total number of them, which I'm going to say is 12, because I put in $1,200 is. I put in $100 for every single month it was there. And then that's minus 1 all over 1.02 minus 1. So let's see. Try it out on your calculator. So you would do the 1.02 to the 12th first. And then minus the 1. And times it by 100. And then the denominator is just what? 1.02 minus 1? Just 0.02. So you divide by 0.02. And we end up with $1,341. Oh, good. Is that what everyone else got? Okay. Why is that so exciting that we ended up with $1,341? How much money did you actually put in?
No.
$1,200.
Oh.
Yeah, you actually put in $1,200.
Oh.
And by the end of it, you walked away with $1,341. Yeah, so you got quite a bit of interest. And the interesting thing is, again, the money you invested earlier earned the most interest, whereas the money you put in recently earned less interest. And so all the $100 is that you put into that account are all earning more or less interest depending on how long ago you put it in. And that's what an annuity is. An annuity means you just keep on putting in a certain amount every month, and then at the end you see how much interest you've earned. Okay, I hope that worked. I realize I kind of stumbled over my words there in the middle. But there we go, that's an annuity. And that's all we need from all of this geometric sequence business. Because now we're just going to get a formula. So everyone ready for our formula? Here we go. Here's a new formula. No, we're not even going to use that geometric sequence formula. That's just what the geometric sequence formula is, and then we have an annuity formula. So here's our annuity formula. Yep. So there's a new formula for us. Maybe I should put it over here. Well, I want to put it where you can all see it. P, gosh, what a terrible letter. P previously was, no, it can't be P. P originally meant principal. Surely they don't use the same letter. Ah, good, they do. Use a different letter. S. S equals, guess what S stands for? What would S stand for? Sum. Because what are we adding together? All those monthly payments, right? We're summing them together. We're adding up January plus February plus March and so on. So S equals R, and guess what R stands for? Good guess, no. The repeated investment, meaning $100 every month. You keep on putting in $100 into the annuity, so the R is the repeated investment of 100. And now you have a fraction where the top is 1 plus I to the n minus 1 all over I. Now let's talk about that. First of all, are you surprised by the exponent of n? Right, no, because like the money you invested in January was $100 times 1.02 to the 10th or to the 11th. So that makes sense that you'd have an n up there because that's how many times you technically multiplied that earliest dollar amount by. Are we surprised by the minus 1? Why is there minus 1 there? Yeah, because you know how every time we had something like this, you had to ignore the 1 and then move the decimal twice? So that's getting rid of the 1 in front. And then we just have to wonder, what does I represent? I is the compounded interest rate. So it's not the yearly advertised rate, it's how much interest rate you're actually getting on each compounding. So who knows what that would be then? Remember, it's inside the parenthesis. It's the amount of interest you actually get at each compounding. So I is equal to R over N. They use the letter I in shorthand, but it's the rate divided by N. That's the rate at each compounding. Okay. Well, there we have it, folks. This is our annuity formula. The biggest difference here is that this formula, the compounded interest formula, this was for a lump sum investment. This is when we were doing a lump sum investment. You just put one amount in there, and then bam, you just sit back and walk away. An annuity is for regular, repeated, putting money in every so often. Okay, we're ready to try one? Okay, it's a very different formula for a very different scenario. Find the future value of the ordinary annuity. Now, ordinary annuity means that when you put the money in and the compounding happen at the same time at the end of each month. So let's just define that real quick. Ordinary annuity. The investment and compounding happen at the end of the month. The end of the month, the end of the year, whatever the time period is. So it's kind of like this. Let's say it's the month of January, and I put my $100 in. This is the 1st, and then this is the 31st. So I put $100 into the bank on January 1st. And so that money is sitting there, and since it was there for a month, they're going to give me interest on it. And on the exact same day, they're going to give me interest on the $100 that I already had there. And simultaneously, I'm going to slip my next $100 into the bank. So now I got two amounts of money riding in there. And then they'll both move forward until the end of February. And then my first $100 is going to receive my second amount of interest. My second $100 is going to receive its first amount of interest. And then I'm going to go ahead and slip another $100 into the account.
That's supposed to be it.
Yeah. Yep. And so that's always happening at the end of each month. They give me the interest on the money I already had there. I slip in an extra hundo, and they all keep riding forward into the future. Okay, that's an ordinary annuity. It all happens at the end of each month. All right. Okay, I think we know what everything is now. Let's just go ahead and do a calculation. So find the future value. Interest is compounded annually and also otherwise indicated. So our R is $100. Our interest rate is 0.1, and N is 6. So what does all that mean? You're going to put $100 into the bank how often? How many times a year?
6.
6 times a year. So every 2 months you put $100 into the bank. And we want to know, what are all of those going to add up to at the end of the year? Find the future value. Yeah, at the end of the year. At the end of putting in your 6 times. That's really what they're saying. By the time you're finished putting in your $600, how much will you have? So let's calculate it. S equals R, 1 plus I to the nth minus 1, all over I. So S equals 100, parenthesis, 1 plus 0.1 to the nth, which is 6, minus 1, all over 0.1. Folks, this is calculator heavy. And can I make a recommendation about your calculator? Yes. Oh, good. You need to use a lot of parentheses. So it's going to be 100, parenthesis, that's the numerator, parenthesis, that's the 1 plus 0.1, parenthesis, caret 6 minus 1, parenthesis, that's just the numerator still, and then finally divide by the 0.1. So that's what it has to look like. You have to have 2 sets of parentheses, an inner parenthesis for the 1 plus 0.1, the outer parenthesis to capture the whole numerator, and then the divide by 0.1. So everybody try typing that in. With all those parentheses, 100, parenthesis, parenthesis, 1 plus 0.1, parenthesis, caret 6, minus 1, parenthesis, divide by 0.1. Did you all get 771? Now, what's the exciting thing about this? How much money did you actually put in? $600, right? You put in $600 bills. And so by the end of it, you had $771.56. How much interest did your first $100 earn? Quite a bit. Quite a bit, because it was in there the whole time. How much interest did your last $100 earn? Nothing. Nothing. The last $100 was just, all right, here's 100 to throw on top. Right, so no interest was earned. But the first $100 earned a lot of interest. The second $100 earned some interest. The third $100 earned some interest. By the end, you just throw the last $100 on the stack and then you're done. Okay, well that was fun. So that's an annuity. That's an annuity. Notice that that's different from a lump sum investment. What would it have been if I just took the $600 and put it in right up front and waited a year? That's worth asking. What would it have been like had we just took the $600 and put it in one lump? We don't need to calculate it, but I want you to just think about that question. Would you get the exact same amount of interest? That would be a different amount of interest. What would be better, the annuity or the lump sum?
Annuity.
The lump sum, because it's getting interest the whole time. The annuity, only that first $100 is getting interest the whole time. And then the second $100 is only getting interest part of the time. So the lump sum would have gotten more overall interest because it was in there longer. Shemai, that's what you said, right? It was in there longer? Yeah, very good. Okay, we can skip number 36 because it's just like it. Let's keep going. Let's just do one more of these. How about number 38? I like 38. So number 38. Now, what's your repeated investment? 2,500. Now, what does that mean? How often am I putting that in? Yeah, it says quarterly. All right, so that's a hefty goal, isn't it? To save $2,500 every quarter. But what does that even boil down to? A quarter is how many months? 3 months. So 2,500 divided by 3 months. That's $833 a month. And most of us get 2 paychecks a month. So that's $416 a paycheck. So that's a lofty goal, isn't it? To save $400 from every single paycheck. That's what this person is doing in order to set aside 25. We're all looking at 38, right? Okay, so they're going to put 2,500 per quarter. They're getting a gigantic interest rate of 0.08. And that's compounded quarterly. Now, actually, keep in mind that I of 0.08, we have to think now, that is the I, I'm assuming, that we actually put into the formula. It's not that they're saying it's 8% per year, which you then have to divide by 4. They're actually telling us I. So they're telling us that's the I. And then it's 16 years. So what would our end value be? Since we're doing it quarterly, and we're doing it for 16 years, how many actual investments are we making? We're doing it 4 times a year for 16 years. That's 64. Okay, so let's write out our formula first. X equals R. 1 plus I to the n minus 1 over I. And so that's 2,500. I just looked at my notes. It is 64, but the I is actually 0.02. That's very misleading, folks. They're really misleading us here. The I, that 8%, they do want us, in fact, to divide it by 4. I'm sorry, folks. I did this out earlier, so I know that it's supposed to be 0.02. So let's do that. We're going to put the 2,500 as our repeated investment. It's 0.08 divided by 4, so that's really 0.02 as the interest per compounding. So that's 1 plus 0.02 to the power of n. The total number of compoundings, as Julie said, is 64 minus 1 all over 0.02. That means we probably got that first one wrong, according to the back of the book, because we didn't divide the 0.1 by 6. And yeah, I think that's what,
No, that's right.
it is right?
Yeah, in the back it's right.
Oh, well, then I'll be,
Because it says it's compounded annually.
This one, that's why it's.
Oh, that one was compounded annually. Okay, that makes
This one
sense.
is quarterly.
All right. So what did we get? Use all your parentheses. So we had 2,500 parentheses, parentheses 1.02, parentheses to the 64 minus 1, parentheses divided by 0.2. Did y'all get 318,936? 0.66?
It's light.
So 38. Yeah, that's it. So I guess we should keep that in mind, that they're using the letter I in an ambiguous way. That in the formula, what they're really wanting is the interest per period, the compounding period, but they're telling us the nominal rate. And they shouldn't be doing it like that. They should say R equals 8%, not I. Okay, so was that a good deal? How many times did we actually put 2,500 in? Quarterly? So we put 2,500 in 64 times, so 2,500 times 64, that's only 160,000. So how much interest did we get?
Whoa.
A considerable amount. Of course, it is 16 years. 16 years is a long time. Remember earlier, the economy, the inflation doubled. How long did it take? 14 years? So I mean, that's roughly double right there, because 16 years is a long time. Okay. Well, let's keep going. So we've done now 2 annuity problems, where we all now know that I definitely has to be the compounded interest rate, not the interest rate that they appear to be giving us. So let's do the next one. How is number 39 different? What are we trying to find now? Yeah, now we're trying to find the periodic payment, which is R. They define R to be I said repeated investment. That could also be a periodic payment. Now this is a fun question. How much money do I have to put aside every paycheck in order to reach my financial goals? This is probably one of the most interesting questions we've seen tonight, because we can all apply this to our life. How much money do I need to save from every paycheck to reach a financial goal in the future? That's what we're about to calculate. So for instance, in number 39 in this scenario, they're saying, I want to have $63,000. Who doesn't? And they have available to me an interest rate of 6%. And it's compounded annually, so n equals 1. And payments are made at the end of each year. That just means it's an ordinary annuity. And we can do this for 12 years. So how much do I actually have to put in? Now, how often are we putting money in? At the end of each year. So we're going to do it at the end of each year. So let's look. S equals a repeated payment of 1 plus I to the n minus 1 over I. And we know we want to end up with 63,000. What we don't know is how much money we have to put in periodically. But we do know, now what's I? I is equal to R over N. So in this case, it's 0.06 over 1. So it's just 0.06. That is actually our I value. So that makes it 1.06 to the N. How many total times? Sorry. N. This N refers to the total number of times. This is the total number of times. Boy, they use letters in an ambiguous way. N typically was referring to the number of compoundings, which is once per year. But how many total times are we going to put money in? 12. So that's the 12 we're looking at right there. We're going to put in this money 12 times. There we go. Boy, they should really use some new letters. Okay, so how do we solve for R? We'll just calculate this whole bit right here and then divide it off. So 1.06 to the 12 minus 1 divided by 0.06. Is that what you got for R? 16.8699. So we divide it off. So how much money do we have to put in? Yeah, $3,000 a year. Now that's actually not a lofty goal, is it? Like, if you want to have $63,000 12 years from now, which, you know, all of us should want to have at least $63,000 12 years from now, we would want to save up $3,700 a year. If you divide that by 12, that's only $300 a month. And if you divide that by 2 paychecks, that's only $150 a paycheck. That's very reasonable. That is provided we can earn 6% interest. Yeah, but still, not bad. Okay, so that's how we find R. That's pretty straightforward. So we're gonna skip 40 and keep going. We wanna keep seeing how to do different things with this. All right, now, they're using this phrase here, sinking fund. That's just a synonym for annuity. Sinking fund. That's referring to the fact that you keep on putting money into this fund. So find the amount of each payment to be made into a sinking fund so that enough will be present to accumulate the following amount. Up over here. Payments are made at the end of each period. The interest rate is given per period. Now notice that. That's very important. They said the interest rate is given per period. Do I believe them? I don't even know if I believe them. Let me look at 41. No, we still have to divide it by the number of compoundings. So 7% twice a year, R divided by 2, that's really 0.035 that we're going to use. I only know that because I already did them and I compared them to the answer key.
So 7% because it's an annual.
It's 7% for the year, but semi-annually means that you're dividing it by 2, so 7 divided by 2 is 3.5. So let's look at this. Find the amount of each payment. So again, what are we solving for? R. So we set it up the same way. How much do we want at the end? Equals R times 1 plus I to the total number of investments, the total number of payments, minus 1 over I. So we want to end up with $44,000. And we don't know how much of a repeated payment we should put in. But we do know that we're going to get 0.035% per compounding period. It's twice a year, so 7% divided by 2 is the 0.035. So what's the total number of investments we're going to make? If we do it twice a year for 13 years?
26.
Yeah, 26 total. And then minus 1 over 0.035. Again, this language is very different. What we're saying is that the 0.035 is the interest rate. That's how much interest you're actually getting at each compounding. And the total number of compoundings is 26. So this is interesting. We're not really talking about years or yearly interest. We're talking about the total number of investments you make and how much interest you're making at the end of each investment period. Okay, so what do we get? $1.035 plus 6 minus 1 divided by 0.035. Did anyone else get 41.31?
Yeah.
Good. And then divide that out.
And then I got 1065.03.
Yeah, $1,065.04. Okay, good. So that's how much money you'd have to put in twice a year for 13 years to end up with $44,000. Now, off the top of your head, folks, what do you think is better, lump sum investing or putting money into a savings account every month? Well, no, that's a good point. Lump sum investing because you'll have more money to invest. But does that mean you're just going to sit around with all this money at your house until you have enough to finally invest? What should you really do? You really should start putting money into the bank every single month. So even though lump sum investing is nice, it's not very often that suddenly we find ourselves with $20,000 sitting in our house. Like, what should I do with this $20,000 that I have in my house? Invest it? Oh, okay. So really, what's the most likely thing for you to do in your life? Spend it. Yeah. No, the most likely thing you should do is an annuity. Everybody should do an annuity. All of you in this classroom right now, me too, we should all start doing annuities because we all can find $100 a month to put into the bank. Okay. Find the future value of the annuity due. What are they asking us to find?
S.
Yeah, S. We just want to find S, the future value. Find the future value of the annuity due. Now, actually, this is different. Sorry, I made a note right here. The future value of the annuity due. Annuity due is a different concept. And this one means that payments are made at the beginning of each period. So now you're actually going to put money at the beginning of each month so that that money will get paid at the end of the month. Can I erase some of this? Maybe. And I believe that's what the term annuity due means. Let's just check. Yeah, annuity due. This is different from an ordinary annuity. So we said ordinary annuity was the investment happening at the end. Annuity due is you put the money in the beginning. So you invest at the beginning of the period. That's good because that means that the very first $100 that you put in is already earning interest that month. And so this formula is a little different. So you might just want to make a big old circle around the word annuity due. And let's make a note that there's a new formula. The formula might even make sense. You're still going to put in your regular repeated investment, but since you're putting money in at the beginning of the month, and that money is already going to earn interest all month long, it's actually 1 plus I to the n plus 1. Why is it n plus 1? Because the first payment's actually getting some interest. And you still subtract the 1, and you still divide by I. And the only difference here is that you then subtract R.
So we subtract R.
That's one periodic amount. So you're multiplying this periodic amount times this whole thing, and that'll grow it very big. But then you subtract out one periodic amount.
And that's like what, the last one?
Yeah,
Because
it
the last
does.
one would still get compounded, right?
Well,
So the investment happens at the beginning and the compounding as well, or does the compounding still happen at the end?
the compounding still happens at the end.
That's
Yeah. Okay, so in any case, this is now just a different type of annuity. It's the annuity due. So let's just try one. So it says here, number 43, we'll all do 43. Payments are made at the beginning of each year for 5 years, 6% compounded annually. So we know what our payment is. That's the 500. That's the repeated investment amount. And since it's compounded annually, our interest rate of 6% is just 6% divided by 1 compounding, so it's just 6% still. So this would be 1 plus 0.06. And how many times are we going to put money in? We're putting money at the beginning of each year for 5 years. So how many times is that? 5. But really it's 5 plus 1. Because that's what the formula says. N represents how many times you actually put the money in. But the formula says you add 1 to it, and then you minus the 1, and then you divide by 0.06. And then you minus out an R. what do we get this time? 1.06 to the 6th minus 1 divided by 406 times 500 minus 500. What did you all get?
2,987.66.
Yeah, 2987.66. I got that. Did you guys get that? So what's the conceptual difference here? An ordinary annuity. Do you remember what happened to the very last $100 that you throw into the bank?
It doesn't
get any interest at all. Whereas with annuity due, since you're putting money in at the beginning of the month, every single $100 that you put into the bank earns interest. So in general, you would expect annuity due to be a little bigger, the total amount. You'll earn a little more money with an annuity due. Annuity due. Because you invest at the beginning, but you still get the compounding at the end. What was that, 43?
Yes.
Yeah. Well, folks, we have about half an hour. We still have more material that we want to get to. So let's just see here, 45 and 46. These are just word problems.
Cross out you.
No, I didn't say cross them out. This little scenario. Bob deposits $5,000 at the end of each year for 13 years. So how many repeated payments does he make total?
So it's, what is it?
13 at the end of each year for 13 years. So he'll do it for 13 times. And it's paying 6% compounded annually. So 0.06 divided by 1 is just 0.06. And find the final amount. So this is just a very basic ordinary annuity or annuity due. He deposits at the end of each year.
Ordinary.
Yeah, this is ordinary. Ordinary is at the end. Annuity due is at the beginning. And what, Julie?
I was saying it's ordinary.
Yeah, it is ordinary. That is correct. So you would use the regular ordinary formula. And now that we've done this a few times, we can really clarify what these letters mean. The N is the total number of deposits, right? That's the total number of deposits that you're making. Whereas I is still the interest for that period. So what's our formula? Did everyone get that? Yeah. You can type it in your calculator and you have your solution.
But if it was compounded, like semi-annually, then we would have to divide the rate by 2.
Yeah.
Like the 13, no, the 13 would also then be multiplied by 2.
Yeah, it would be.
Okay.
Yeah.
Like 46.
And so did we all find that the answer was 94,410? Oh. All right. 47 and 48.
Put everything in C. I mean, in C.
Let's do number 27. Sorry, 47. So does everyone have all of these formulas now written down somewhere? That this is the ordinary, which means at the end, and then this is the annuity due, which means at the beginning, So that's equals my goodness. Hey folks, what do you think? Should I make you memorize all the formulas for the test?
How about that?
No, I don't think so. I think we'll just put all the formulas up here just like we have now, and your job will be to use them. That would be your job. Is how to actually use them and apply them appropriately. Okay, so we've covered that. So we're all looking at 47. This is a fun question. It says, which of the following investments is larger after 20 years? If you invest $200 monthly and it's compounded monthly, or $2,500 annually and it's compounded annually. Now, everyone, let's change this problem. So the first one, A, is the annuity, right? Is it ordinary or annuity deal? It doesn't say, does it?
No.
Let's choose ordinary annuity. Ordinary annuity. Whereas in B, this is a lump sum, right? Oh, no.
No, because it's still after 20 years.
Oh, so both of these are annuities. It's just that one is annual and one is monthly.
Mm-hmm.
Okay, so
The
it's
monthly one is a smaller amount monthly, whereas the annual is a bigger amount.
yeah, so they're both ordinary annuities. Well, let's change it to 200 monthly and 2,400 yearly. Because that way we're actually seeing apples and apples up yearly, right? Because how much money are you putting in every year? 2,400.
How is that different from 25?
Because I'm saying 2,400.
Mm-hmm.
I'm saying if you put in 200 monthly, 200 times 12 is
Oh,
2,400.
that's why you changed it.
Yeah, so I think that'd be more interesting. Let's actually compare. You're going to put 2,400 into the bank no matter what. Which is better if you put it in every month or you put it in every year? All right. And otherwise, let's see. So we're going to use our ordinary formula. So S equals R, 1 plus I to the n minus 1 over I. And so in the first case, what was our interest rate? Well, the rate is the same. R is 0.0875. And what is n? The original n, the compounding, is 12. And so I is equal to R over n. So what's the actual compounding interest rate? 0.0875 divided by 12. Did we get 0.0072916 repeating? So that's how much interest you're getting at each compounding interval. And the total number of deposits, since it's monthly, for how long? 20 years. So the total number of deposits is what? 20 times 12? Yeah, 240. So those are the two numbers that we need to put into our ordinary annuity formula, which is S equals 200, 1 plus 0.00726, power of 240 minus 1 over 0.0072916. Does everyone agree with that and see where those numbers come from? It's unfortunate that they use the letter N in two different ways.
Is it just the 6 being repeated or is it the 1?
Just the 6. Yeah. In order to calculate I, we're doing the yearly interest rate divided by the number of compoundings per year. But then this N value in the annuity formula is the number of deposits you're actually making. How many times am I actually depositing $200? 12 times a year for 20 years. Okay, so now let's find out. Okay, did everyone get the 129?
Mhm.
412? All right, so that's if we spread the 200 out throughout the year. Whereas what would it be if it were yearly? Now we're just throwing 2,400 in, and we're only doing that how many times? 12 times. No, 20 years, so 20 times. And we're getting the full 0.0875 interest. 20 times. Did I set that up right? Are we surprised by the result? Wait, not? I thought previously we said that lump sum investing would be better to put a larger amount of money in to let it sit there the whole year rather than putting the little 200 in every month, because the 200s at the end of the year aren't getting as much interest as the 200s at the beginning of the year. How do we account for this? That the monthly annuity, you actually ended up getting more. Right? Doesn't that contrast with what we said earlier? Well, keep in mind we did an ordinary annuity, right? So when were we getting the interest? Or when did we invest? Yeah, when did we get the interest? At the end. And we put the money in at the end. So that very last 2,400 that we put in, how much interest did it get? Nothing. Got no interest.
Why I got a different answer?
What, Carmen?
Why I got a different answer?
You did.
I got like 1, 2.
Did anyone else get 119?
I got the same answer as you.
What did you get, Izzy? Carmen, double check your calculations. Plug it in again. Yeah, so in terms of the monthliness, more of our payments had the opportunity to be in the account rather than that last 2,400 that went in and didn't get interest.
For B, are we doing B?
Yeah, we're doing B.
That is 2500.
We all just agreed to do 24 instead.
Oh.
You might just not have heard me say it. I only said it once, but I wanted the 200 and the 2,400 to represent the same amount of money in a year.
Oh, okay.
Yeah, so that's the only difference, Carmen. Yeah, if you change it to 24, I bet you'll get the same. All right. Well, I hope right now we at least all have the feeling that you're going to go out tomorrow and start an annuity. Are you all going to run out to your local bank and start an annuity? Say, hey, bank. No, I mean, besides, don't you all have direct deposit with your paychecks? If you have direct deposit with your paycheck, you know what you can tell your bank? To just start doing an automatic withdrawal of $100 a month and putting it into a savings account, and that'll be an annuity. Your bank will do that automatically for you. I have my bank set up to automatically transfer $50 a week into my savings account. It feels good. I could have made it $200 a month, right? But $50 a week, I'm like, yeah, I'm putting some money in there every week. So why don't you go down to your bank and set it up? It'll just be an automatic payment every single week or month. You're putting money in the savings. Until what, Shemai?
I said you don't even realize it's gone.
Yeah, you don't even realize it's gone. You really don't. All right. Skipping on ahead. Where are we at? Wait, what?
See, it's sitting there in that account. Now.
When I go, what can I do with this?
Yeah, until you realize it's there. Yeah, that's fun. All right, so I do want to talk about. All right, good. All right, let's do these last two problems because 49 and 50. These are good. These are retirement questions, well worth looking at and doing. We all want to have a certain amount of savings in our retirement account. So let's learn about Larry. He wants to start an IRA that'll have $610,000 when he retires in 30 years. So that's his goal. He wants to have $610,000 30 years from now. How much should he invest semi-annually to do this if the interest is 5% compounded semi-annually? Now, first of all, folks, what would you tell Larry? If he really wants to save money, should he only do it every 6 months? How often should you do it? Every darn month. Or every week, right? Just keep on putting that money in there. As often as possible, you won't even notice it's gone. But anyway, he's only going to put it in every 2 months, every 6 months. So it's an IRA. I think we're assuming that this is an ordinary annuity. Do we have any indication? Yeah, I did it as an ordinary annuity and it matched the answer in the back of the book. To be fair, does the problem tell us?
No.
So if we did it either way, would we be wrong? No, we're just solving a problem. Who cares what the answer key says? So let's do the ordinary annuity. So with an ordinary annuity, we want to know how much to put in so that in the end he'll have 610,000. And so how many total investments is he going to do? How many total deposits? 60. Twice a year for 30 years, so that exponent is 60. And he's getting 5%, but it's compounded semi-annually, so it's really
0.05. Oh, 0.025.
yeah, 0.025, which is the top end line. I hope we're all feeling better about the two different ends. This end is the total number of deposits. This end helped us calculate the interest rate per period. All right, so now we're about to tell Larry how much he has to invest. 1.025 to 60. Did you all get 44.85?
Yes.
Okay, now let's do Larry a solid. Let's go ahead and calculate if he did it monthly. So he has to set that amount of money aside every 6 months. And just real quick, I'm going to go ahead and divide by 6. That's the equivalent of 747.60 cents per month. That's the equivalent. So now let's actually do the problem for monthly and see if there's a difference. So the exact same problem, but we'll change it to what? Now it's every single month. So 5% compounded monthly, you take the 0.05 and divide it by 12. So now we're doing 1.00416 repeating. And since you're doing it 12 times a year for 30 years, how many deposits are you making? 12 times 30? 360? All over the 0.00416 repeating. So keep in mind, all we're changing now is the first scenario, he was putting the money in twice a year. Now this scenario, he's putting it in every month. And we're wondering, is there a difference? Should he do it every month or should he do it every 6 months? And I got 731. So what does that mean? This is interesting. If you literally put the money aside every month, how much do you have to put aside every month? 731. But if you're going to wait to only put the money aside every 6 months, how much do you have to save actually every month in order to have that much? 747.
Because of the compound.
Yeah, because of the compounding. So, I mean, how much more money is that? 16 bucks? So he's wasting $16 a month for 6 months, which is $64. He just wasted $64 by only putting money in every 6 months instead of putting money in every month. And honestly, is Larry going to have that at the end of 6 months? He's going to have spent it. Huh. He's going to see that money sitting there doing nothing. He's going to spend it. He's not even going to have it. Whereas, is he going to be able to put this aside every month? Yeah. So that's like a double whammy. do a monthly annuity because you can put the money aside. If you wait until the end of 6 months, you're not even gonna have it anymore. You will have spent it, there's gonna be an emergency, you're gonna spend it on something, right? And what?
And we could do that for every 2 weeks, and that's probably gonna be easier to.
Yeah, if you put the money aside every 2 weeks, then, or just put the money aside every day, then it's even less. You just do it every single day.
Every day is difficult because you don't go to your bank every day.
Well, that's
Every
true.
2 weeks.
Okay, well, number 50 is the same problem. Okay, folks, we are now down to the wire here.
Okay.
Yeah, down to the wire indeed. So let's just think about what we're gonna cover from 5.3. In here, 5.3 was asking about, what if instead of doing a monthly annuity, you just did one lump sum at the beginning? What would that difference be? One lump sum at the beginning versus an ordinary annuity. So I think I would definitely like to try that. Find the present value of the ordinary payments of that. Yeah, okay. Find the lump, oh, here we go, skip to number 53. You can cross out what you want to do.
Like, I'm cussing with a passion.
Yeah, with the fury. So, this is a great question. Find the lump sum deposited today that will give you the same amount as a yearly payment made at the end of each year for 20 years at the given interest rate. So, here's what they're saying. You could, number 53 says, deposit $600 per year, how long? For 20 years. Right? Now, just off the top of your head, if you weren't going to earn any interest at all, how much money would you have by the time you're done? 12,000? 600 times 20? I mean, no matter what, you're going to have $12,000 or more if you're earning interest. So no matter what, you just got $12,000. But then if you tack interest on top of that, first let's find out how much we would actually earn. So how much is this ordinary annuity going to give us? Let's find out. Let's calculate this ordinary annuity. We know the formula, S equals R, 1 plus I. So our payment is $600. We're going to do 20 of them. And what's our interest rate? 3% is compounded annually, so it's 1.03. So the first thing is just how much money would we have at the end of these 20 years with this ordinary annuity? 1.03, yeah, that's fine. And how much did we get? Yeah, 16,000. So that's nice because without interest, all we'd have is the 12,000, but we got 16,000. So now the question is, how much would I have to invest now? Just right up front today, so that at the end of the 20 years, I'll have 16,000. How much do you think I'd have to invest now? Now, Nick's joke answer would be 16,000. And by the end of it, you'd have the 122. Well, let's find out. This is the actual way to calculate Nick's joke from the beginning. All right, so here's Nick's joke formula. It's the lump sum formula. It's how much would you have to invest today to get the same amount of money as doing the $600 annuity. So here it is. The lump sum would be R. There's that saying, what would be equivalent to the $600 payment. The formula is the same but different. 1 minus 1 plus I to the negative F all over I. What changed in this formula from our ordinary annuity formula?
I'll say one's positive.
Yeah, we switched the order. Instead of 1 plus I to the n minus 1, we did 1 minus 1 plus I to the n. And then the n is negative. We'll just finish this problem, and then we'll talk. And that is going to tell us how much I would have to invest today to have the same amount of money, 16,122, as if I had done the annuity. So let's find out. How exciting. 600, 1 minus 1 plus the 0.03 to the negative n. So that was a negative 20 over 0.03. Let's find out. So 1.03 to the power of negative 20. Be very careful that your exponent, you put a parenthesis, negative 20 parenthesis. And then 1 minus that. Be very careful. Then divide by 0.03. Then times 600. Nick, you're going to be shocked. I know you're just waiting for me to write down the number. 8,926. Nick has a renewed sense of faith in the investment system. So if you had $8,926 today, and you just threw it in the bank and waited 20 years, you'd have 16,122. But you know, the question is, what do you really have? Do you have 8,926 today, or can you put together 600 bucks by the end of this year? I mean, you probably just can put together the 600 by the end of the year. We don't have this sitting around in our pockets. But that's pretty cool. So we call this the present value of that annuity. The present value is $8,926, because if I had that much money now, I'd be able to invest it and get this annuity. But since I don't have this much money now, I'll just scrap together 600 bucks by the end of this year, invest it, and I'll keep doing that every year. Well. That brought us right up to number 55, which was about loan amortization. And there, you know, we just had what, 3-4 more pages where we're going to do loan amortizations. Yeah, so obviously I can't put loan amortization on the test, so I won't. Right, and so here's what I'm committing to do for you. It just might take me all night. I'll go to bed by midnight, but I'm going to do this for you. So first, I'll go into my math lab and delete the problems that we didn't get to. Okay, so I'll just click, and I'll delete anything that we didn't even get to. Next, I'm going to make your practice test, and I will send you the practice test by email in a PDF. So because I didn't know how much to include on the practice test, I didn't already make it and give it to you right now. So you will all have to just go print it yourself.
But give it to us tomorrow.
Yeah.
You will be understanding.
It'll only be like 4 or 5 pages though. Right? The practice test and the test before was 5 pages. So it'll just be 5 pages, and you can go to the library and print it for free, or you can print it at your home computer, whatever you want to do. Okay, does anyone have any questions before we leave? Does that cover everything? Everyone feels good about everything?
So we don't have to do the rest of the problem.
Right, you don't have to do the rest of the problems.
Oh, yeah. Oh, I'll just put on the package.
Thank you for ordering.
You're welcome.
What did they all just go? Did they already pack up? They didn't pack up, they're just walking.
No,
Oh, Nick left? Oh, Nick and Julie. Okay, but then Lorena left, but she has all her stuff here.